Hey, Harsh here. Today we are going to be talking about message queues. Before we look at these tools, we need to clear up the biggest source of confusion in system design. We often use the word messaging to cover two completely different concepts: queues and streams. Imagine you're managing a restaurant. A queue is like RabbitMQ or SQS is like a ticket wheel in the kitchen. A waiter writes down the command like table 4 needs a pizza and sticks it on the wheel. A chef pulls the ticket, cooks the food, and throws the ticket in the trash. Once the task is done, the message's life is over. A stream like Kafka is a completely different concept. It's like a restaurant's security camera, cash register log combined. It records an immutable ledger of facts, like customer walked in at 12:01, burger ordered at 12:05. The kitchen can read this and cook the food, and the accounting department can read the exact same ledger later to calculate the revenue. The data isn't deleted just because someone read it. In a queue, the broker is stateful and tracks what has been read. In a stream, the broker is like a dumb pipe, and the consumer tracks its own read position, known as its offset. If Kafka is a dumb pipe with smart consumers, RabbitMQ is a genius pipe with dumb consumers. RabbitMQ operates on a traditional queue-based architecture using AMQP protocol. In RabbitMQ, producers don't send messages directly to queues, they send them to an exchange. Think of an exchange like a highly efficient post office sorting room. You configure bindings, which are rules that tell Exchange exactly how to route these messages to different queues. For example, you have a topic exchange where a web portal publishes a JSON payload with a routing key like priority.high.server. You can bind a DevOps queue to catch anything matching star.server and completely separate PagerDuty queue to catch priority.high.hash. RabbitMQ handles all of this complex routing out of the box. Once a worker grabs the message, RabbitQ holds its breath, waiting for an acknowledgement before permanently deleting the message. If the worker crashes and the TCP connection drops, RabbitMQ simply handles the message to the next available worker, ensuring no data is deleted. However, because it tracks all the state in memory, if queue backs up into millions, it has to page to disk and performance will fall off a cliff. Now let's talk about Kafka. Kafka is not a traditional message queue, it is like a distributed event streaming platform. It was born at LinkedIn to handle massive, relentless pipelines of data. Internally, Kafka persists messages in immutable, append-only logged. To achieve its insane scale, Kafka splits topics into partitions. A partition is a fundamental unit of parallelism. If you have a topic getting 50,000 events a second, you can split it into 20 partitions spread across 20 servers, meaning each server handles only 2,500 events a second. Kafka achieves SSD like throughput even on spinning hard drives by utilizing sequential I/O. It just appends bytes to the end of the file, avoiding the slow random reads of traditional databases. Because data is retained on a disk rather than deleted upon consumption, Kafka introduces consumer groups. A consumer group is a set of applications coordinating to read a topic, and each group manages its own offset, a bookmark indicating exactly which message it read last. This enables Kafka's superpower, which is replayability. If you deploy a bug that corrupts your database, you can fix the bug, rewind your offset to last Tuesday, and seamlessly rebuild your state. If you want absolutely zero operational overhead, you turn to something like an SQS. SQS is the oldest service in AWS. And while it doesn't have this fancy routing of RabbitMQ or the replayability of Kafka, it provides a quite scalable, highly efficient buffer with a single click. Unlike Kafka or MQ, you do not hold open persistent TCP connections with SQS. Your workers make HTTP requests to AWS using a technique called long polling. When a worker pulls a message, SQS relies on visibility timeout. If the timeout is 2 minutes, SQS makes that message invisible to all other workers for 2 minutes. While your worker processes it, If the worker completes the task and deletes the message, great. If the worker crashes silently, the timeout expires and message magically reappears in the queue of another worker to try. However, there is a trap here. SQS charges per request. If your architecture relies on constantly polling empty queues, or if you grab messages, decide you aren't ready to process them and put them back, AWS will charge you. Whenever you work with distributed systems, you have to talk about delivery semantics. System usually promises one of three things: at most once, at least once, or exactly once. At most once is fire and forget UDP style, where it's okay to lose a message like dropping a single frame of live video metrics. At least once is the industry standard. The broker will keep delivering the message until the consumer acknowledges it. If your worker processes a payment, the network drops acknowledgement back to the broker and the broker will send the payment message again. This brings us to exactly once. True end-to-end exactly once delivery across external networks is a mathematical impossibility. Kafka can do it, but only for Kafka to Kafka workflows using complex internal transaction APIs and sequence numbers. The actual reality is that you must build your consumers to be idempotent in nature. Idempotency means that if a consumer receives the same message 5 times, the business state only changes once. You achieve this by generating a unique ID for an event and having a consumer check a database to see if that ID has been already processed before taking an action. To wrap this up, your job as a dev isn't just picking the coolest technology, it's matching the semantic design of a tool to economic and technical reality of something that you're making. Remember to differentiate between commands and events. If it's an ephemeral task, use queue. If it's a permanent fact, use a stream. Stop trying to achieve exactly once delivery over the network, and we have to embrace something like at least once delivery and build idempotent consumers. And above all, we need to understand the cost model of all of our cloud services. A simple managed service like SQS is fantastic, but paying per request is quite expensive. And often the best decision is something like Kafka acting as your high throughput central system with RabbitMQ for microservices or queues. It's super complex, and you only need these things when the scale grows to a massive, massive volume. For normal tasks, for normal projects, you don't really need to look at this kind of stuff. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.